Okay guys, so today, if you guys still have cell phones out, those need to be put away, please, and thank you. Okay, so today we're going to talk about something called Trig Identities. Gentlemen at the back, are you ready? Okay, so today we're going to talk about Trig Identities. One more time, still waiting. Okay, but firstly it would be helpful if we know what is an identity. So this isn't on your lesson, but if you feel like you would like to record this information, there's a little bit of space down at the bottom in the back of your lesson. So an identity. So firstly, we need to know that an identity is an expression that's true for all values of, we can say, of the variable in the equation. So it's usually like one variable, but an expression that is true for all values that could be inputted or should I say input? That should be input, inputted, whatever. Yeah, I probably should say input. Sorry, this is all messed up. That could be input into a variable in an equation. I shouldn't say equation, expression. Sorry, I just want to get the wording right. Sam. Okay, so an expression that's true for all values that could be input into a variable in an expression. So usually it's talking about the equivalency between two expressions. So an example of one specific trig identity is one that we use very often is we say the tan of theta or of x is equal to the sine of theta over the cos of theta. So you'll notice here that this is actually different from some other trig expressions and trig equations that we've been solving. So an identity doesn't need to be solved. An identity is just an expression that says one thing is equivalent to another thing, no matter what value we put in for theta, as long as it's all the same. So we can do a couple little tests here. Julie, can you choose me an angle? Can be any angle. 39. Okay, so grab out your calculators in degree mode. We are going to evaluate the tan of 39, and I want to see what that decimal is equal to. So what did you get? Tan of 39?
0.809781. Oh, 84.
And so on. Sure. Now I want you guys to try the sine of 39 divided by the cos of 39. This is all degrees. And I'm going to show you that each side is equivalent here. So I want to see if the sine of 39 divided by the cos of 39 gives us that 0.8097 whatever value. What did you guys get? The same thing. Okay, and that's because these expressions are equivalent no matter what theta we choose. So Jolie just chose us a random value for theta, and as long as I plug in the same value of theta for all of those things, take one of each, my expression holds true. So it's an expression that tells us that one thing is equivalent to another thing. Okay, make sense? So this is different than an equation, okay? For an equation will tell us that for some value of theta, let's use the example of tan again. For some value of theta, tan equals, let's say, 0.75. Now this is only true for one specific, or maybe two because of the cast rule. It's only true for certain values of theta. It's not true for all values of theta. So that's the difference between an equation and an identity. Your identity is going to be true for all values of theta, provided you plug in the same value for each of them when you're testing the expression. And an equation is only true for the values that you solved the equation to be true for, right? So this is only true, this is an equation and not an identity because this is only true for some values of theta. And those would be values of theta that we would have to solve for. Okay, so identity versus equation. Identity is true for all values of your variable. It can be theta, it can be an x, it could be a y, whatever, doesn't matter. And it's showing you that something is equal to something else, okay? So in this case, the example that I gave you, tan of theta is equal to sine of theta over cos of theta for any theta I could possibly ever choose. But if we have an equation is only true for some values of theta that have to be solved for. Another example of an equation that's not like a trig equation could be x plus 2 equals 5, right? This is not true for all values of x, right? This is only true when x equals 3, and that's why this is an equation and it's not an identity. Okay? So just so we have that kind of down before we start today. Good? All right, so I handed you guys out a little slip of paper, and it is the fundamental trig identities. So these are identities that we know are true. I'm just going to put them up on my screen here as well so everyone can see it who's watching the video. Okay, these are our fundamental trig identities. These are a set of identities that we're going to work with in grade 11. There are actually more that we know are true. But these are going to be the main ones that we work with this year. And we actually already know some of them. So we actually already know the reciprocal identities. We know that cosecant is the reciprocal of sine. We know secant is the reciprocal of cosine. And cotangent is the reciprocal of tan. These ones we don't know yet. Now we do know. So I just showed you guys that tan is equal to sine over cosine, so long as those variables that we put in the sine and cosine and tan are the same. And if cotangent is the reciprocal of tan, if tan is equal to sine over cos, then cotangent must be equal to cos over sine. These ones are called Pythagorean identities over here, and they are basically additions. And be aware that I can take maybe one of these terms and I can move them to the opposite side of the equal sign. So I cannot rearrange some of these Pythagorean identities if I need to. So there's a couple different things that we can do to these identities, and I'm going to show you in the tips and tricks section of your lesson some different things that we can do with these to rearrange them. Okay guys, stop or you're going to be moved. Okay, so let's jump over to the lesson today. One other thing that you just kind of need to know as far as like setup for this lesson is we're going to do something called a proof, and this is kind of the first time that you've probably been introduced to something like this. And the idea is when I'm solving different trig identities, ones that I don't know for sure, like the ones that are not on this page, we're going to use identities on this page to prove other ones. And when I prove them, basically what I do is I take the left side of the equation and I write it separate from the right side. And then I'm going to do some work. I'm going to maybe do some substitutions with my identities. I'll plug things in and I'll work maybe just on one side, maybe I'll work on both sides. But we don't cross over this line. So for this line right here, this is a line that's going to completely separate our work. Okay, so when I do a proof, I don't treat this line as an equal sign anymore. I don't say, okay, I can do to the left side what I do to the right side. I work with the left side completely separate to the right side. And my goal in this is trying to make the left side equal the right side in the end. I want them to both end up being exactly the same. Okay, so this math is a little bit different than math that you've done in the past. The only way you get good at this is if you practice, because there's no way I can possibly show you all of the different types of things that you'll be approached with. But this is essentially how we're going to set up. We'll do some work, maybe on both sides, maybe just on one, whatever. And our goal is at the end to have equivalent expressions on each side. So maybe I have a sine theta on the left side and I have a sine theta on the right side. I want them to be equal to show that this expression is true. And then at the end of my proof, the setup goes like this. We say left side equals right side. Basically just says like the proof is done. I've shown that left side equals right side and I've proven it. It's true. And then there's a couple things that you can do. So usually I do little box, and this is kind of like the mathematician's way of like bragging that we're done the proof. We're like, yep, we squared it away, the proof's done. It's our like, yes, we did it kind of thing. You can also say IIP, which means identity is proven. Sorry. IIP. Or you can also say QED, and QED is the short form for a Latin phrase, and it essentially just means the translation in English is just which was demonstrated. So this is kind of like a Latin phrase meaning, well, it's not a Latin phrase in and of itself, but it stands for a Latin phrase meaning which was demonstrated. So you can choose either one of these three. You might see on some of my files I use like QED. For the most part, lately I've just been using the little box. It's really quick. But you have to choose one of these three. They can be your little humble brag that you finished the proof and it's all good. Okay? Also, every single time I do work on the left side and the right side, I'm going to make sure I have equal signs on each of my steps all the way down. So this is just like setup kind of stuff. Okay, just like in your regular math, if you're working with an equation, you're saying equals on every single line as you go down. Okay, so I'll of course show you an example of this as we go further. Is that what you're going to ask? Yeah, so don't worry. This is just kind of like setup stuff right now. Okay. Couple tips and tricks that I think will be really helpful for you guys before we start some of these questions. And again, some of the stuff will make more sense once we actually start to do questions. But I would say the biggest tip that I have for you when you're solving and proving, not solving, I shouldn't say that, when you're proving trig identities is we want to get everything, there's lots of different trig ratios that we can use, right? We have 6 different. So if I can funnel these all down in terms of like 1 or 2 trig ratios, that will be really helpful for me. And I would say probably about 95% of the time that you do proofs, it's really helpful to turn everything into terms of sine and cosine using your identities on your sheet. So that's my main tip. So we will usually, I would say this works again 95% of the time, start by changing everything into terms of sine and cosine. Okay, the x's are just variables here. They can be thetas, they can be anything, doesn't matter. But they're x's on your identity sheet, so I'm just putting them as x's here. Okay, this is the biggest tip. If you ask me a question on a proof and you haven't done this already, that will be what I tell you to start with. Okay, so this is the very first thing that I usually always do. Okay. We can also rearrange some of our trig identities. And what I mean by that is, for instance, take the Pythagorean identities. So if you look, yep?
Is this the first introduction to the trig identities?
Yes. Okay, so if you look at your sheet, your little skinny sheet there, look under Pythagorean identities, and you will see that sine squared x plus cos squared x equals 1. Okay? This is an identity, but it works similar to an equation in the sense that I can move terms to the left and to the right as long as of the equal sign, as long as I change their sign. So one rendition of this, one rearranged version of this, is if I took cos squared x and I moved it onto this side, I would have sine squared x, and what would cos squared x become when I bring it over to the opposite side of the equal sign? Yeah, it just becomes negative cos squared x. So this is one rearranged version of that Pythagorean identity. I'm going to ask you guys right now to actually add this directly onto your identity sheet because it's used very, very often. It might even be used more than this original Pythagorean identity itself. So add it onto your skinny sheet off to the side. Okay, sine squared x equals 1 minus cos squared x. And the other way I can rearrange this is if I take this sine squared x and I move it onto this side of the equal sign, it becomes cos squared x equals 1 minus sine squared x. And I'm going to ask you guys to add this identity to your sheet as well. Okay, because it's used quite often. So I can actually do this with any of the Pythagorean identities. So you guys see that we have secant squared x equals 1 plus tan squared x. I'll just throw it up on the board for you guys here. I can move each of these terms freely so long as I switch their sign as I move them to the opposite side of the equal sign. Same thing with cosecant squared equals 1 plus cotangent squared x. Okay, so I can move this over, and cosecant squared minus cotangent squared is equal to 1. That kind of idea. Okay, we can also take a look at our reciprocal identities and our quotient identities, and there's some work that we can do with those guys as well. So for instance, this is one that's used quite often. Okay, I can also think of this as kind of like how we use an equation, and that is like if I do one thing to one side of the equation, as long as I do it to the other, it's still an equivalent identity. So if I happen to square both sides of this equation, I can see here that we get tan squared x. And then when I square a fraction, I square the top and I square the bottom. So tan squared x is actually equal to sine squared x over cos squared x. So that kind of idea. Tan cubed x is going to be equal to sine cubed x over cos cubed x. So same kind of trend that we're following here. I'll ask you guys, you might want to add this guy to your sheet as well, because this one is used quite often also in our solving. Yep, Sebastian? So this is going to help us. These are just some tips that will help us later. But you'll kind of understand once we start doing questions. Okay, you should also be aware, so this can be done also with cotangent equals cosine over sine. So cotangent squared is equal to cosine squared over sine squared. That still holds true. I can also do this same thing with my reciprocal identities. So for instance, if I take cosecant x is 1 over sine x, and then I square both sides of this expression, just like we did above, I get that cosecant squared x is equal to 1 squared, which is 1, over sine squared x. So just squaring the top and squaring the bottom here. Okay, so we can also do this same thing with all of the reciprocal identities. Okay, so if you want to just add that to your sheet, you can add that to your sheet as well. And that's true for secant and cotangent as well. It will just be like secant squared equals 1 over cos squared, and cotangent squared equals 1 over tan squared. So that kind of idea. Okay. Difference of squares can be helpful when you're doing trig identities. Difference of squares, if you guys remember, is two terms that are perfect squares that are being subtracted. So I'm going to give you an example of a difference of squares that is not trig related. And that would be something like 9x squared minus 16y squared. Does anyone remember how we factor this guy?
Square root the first term, square root the last term, and
Very good.
do a plus and minus.
Awesome. So we square root each term. So the first term's square root, which is 3x, will go in the first space here. And the second term's square root, which is 4y, will go in the second space here. And one bracket has a plus, one has a minus. And this is now factored. So you might notice that you come across something that has something kind of similar to this, where you're subtracting two squares. And you should know that you can actually factor and FOIL these. So I can either go from factored form into expanded form, or I can go from expanded form into factored form, depending on what I need. So just as an example, one that we use quite a bit is these two guys up here are actually differences of squares, because one is a perfect square, and cos squared and sine squared are perfect squares as well. So if you happen to notice something like 1 minus sine squared x, can somebody tell me how we could factor this? Yep. So we take the square root of the first, which is 1. We have a plus and a minus, and the square root of sine squared is just sine x. So this actually factors into 1 plus sine x, 1 minus sine x. That's kind of the idea. Yep. Okay, so this technique can be helpful as well. All right, so we may add to some of this tomorrow. In tomorrow's lesson, just a couple extra tips and tricks as you guys start, but I think we're just going to start with those ones, and then we'll see what we can do from here, okay? So main step, we're going to start by changing everything, replacing things with their equivalent identities as much as we can by changing to sine x and cos x. That's the big thing. Okay, so let me just kind of show you now what I actually mean. So here's our task. We're tasked with proving this trig identity. So we're not solving it. Remember, we're just proving by simplifying and replacing some of these things with our identities on our sheet. So these identities here, that we can simplify this to equal 1. Okay? So here's how we're going to set up. This is already partially set up for us just to kind of get us going. We're going to separate the left side and the right side completely. So I'm just going to start by rewriting the left side and rewriting the right side exactly as they are. And now that I've done this, you cannot cross things over either side. You cannot square both sides. You can't do any of that. Okay? So we're working with these completely separately. Okay, so 1, there's not a lot that I'm going to be able to do with that. So usually my best course of action would be to start with the more complex looking side. So we're probably here going to start with our left side. The main step that I told you guys about is we want to try to get everything in terms of sine and cosine. So cosine is of course already in terms of sine and cosine, and so is sine. But tan is not yet in terms of sine and cosine. So tan x, can you guys look at your sheet and see if you can find something for tan x that we can use to sub in that's maybe already in terms of sine and cosine?
Tan x equals sine x over cosine.
Okay, so tan x equals sine x over cos x. Does everybody see that on their sheet?
Yes.
Okay, so I'm actually going to come in here and I'm going to replace tan with what it's equal to. It's equal to, I'll do it in another color so everyone can see. It's equal to sine x over cos x. So I'm actually replacing tan x with its identity from our identity sheet here. So I know tan x is equal to sine x over cos x.
Wait, how do you know if this is equal? Where's
So this sheet
yeah.
here, these are standard identities that we know are true for sure. So this is kind of like our little catalog, and we shop in this to see like what I can plug in where in some of my new identities that I'm proving.
Okay, so what did you just replace sine?
So I'm using this. Sorry, let me just get my stylus here ready. So I'm using this guy. Sorry, again. I'm using this guy. And I'm saying because we have tan x in our equation, I'm replacing it with what it's equal to, sine x over cos x. Okay? Everyone's on board? Everyone's good? Okay. All right. So I just replaced that with its identity. And now I would kind of like to just go through and maybe simplify this expression. I want to eventually, if I'm looking where I'm headed here, I want this to eventually equal 1. Okay? So does anybody see anything that we can do to maybe simplify this expression a little bit? Maureen? Not yet, but maybe in a step. Can we focus in on the top here? If this is cos over 1, what do you see with these coses? Yeah, these can be crossed because they're being multiplied, right? So we know we can cross any top out with any bottom. What's left on top? Okay, and anything divided by itself is equal to 1. Cool. So we end our proof proper form. We say left side equals right side, and we do our little humble brag of putting our little square there, just to give ourselves a pat on the back and say, we did it. Questions? Anything? Are we all okay so far?
Wait, what happens if I drew a triangle?
Why do you put a square?
0 out of 5. Little square is just a sign that the proof is done. Okay?
Yeah, what if
Cool?
you want to be humble?
That's the humble brag right there. That is being humble. Okay, we're going to try another one. I'm giving you some easy ones to start out here, okay?
Thanks, Mr. Caleb.
You're welcome. Okay,
Just easy ones for the rest of uni.
no. So these ones use theta. If you guys want to, you can replace your thetas with x's if it makes you happy, since your identity sheet has all x's. But if you're going to use thetas, just make sure you stay consistent with using all thetas. So if I'm going to use theta, I'm just replacing all these x's with thetas. That's all that it is. Okay? So main goals, okay, are turn everything in terms of sine and cosine. And you're probably going to start with the more complex side. So which side would you guys start with?
The left side.
Okay, so we'll probably start with the left side. I already have sine theta here, so that one I can keep. What about secant theta? Can you guys see anything on your sheet that we might be able to replace secant theta with? Elise, what do you see? Okay, so we have secant x right over here. It's equal to 1 over cos x. So I'm actually going to go ahead and I'm going to replace this secant theta with 1 over, it's cos x on our sheet, but because we're using thetas, it's going to be 1 over cos theta. Okay, you'll see that on the left side of your sheet there. Okay, how about cotangent? Can somebody find something on their sheet that we can use for cotangent? What do you think, Sam?
1 over 10x.
So that's an option.
Cos x over sine x.
Okay, I will tell you guys, I rarely use this identity right here because if I'm trying to get everything in terms of sine and cosine, this is probably my more effective identity, right? So I usually defer to using that middle one. You can still get there, but you're going to have to do a couple more steps if you sub in 1 over tan x. Doesn't mean I never use it, but usually I'll end up using this one. So cotangent x is equal to cos x over sine x. And because we're using thetas, it's going to be cos theta over sine theta. Okay, thoughts as to where we can go from here? Elise?
Can't you just like put the 2 brackets and then it becomes like sine theta and then times like cos theta squared?
Not, well, the cos is on top, so I don't think we're going to get a cos squared theta. Ivana?
Cancel your cos and sine.
Okay, so I have a cos on the bottom and a cos on the top. It's all being multiplied. And then I have a sine on the top and a sine on the bottom, right? So these will all cancel. So what are we left with? 1. And we're done. You can say left side equals right side.
And a square.
And a square. That's right. Then you can be happy. Okay, questions on this example? How are we doing so far? Is this all right? going to get a little bit harder. Okay, let's try another one, and then we'll take a quick break, okay?
Yep.
Okay, left side and right side. So we're going to start by just rewriting what we have on the left side and what we have on the right side. Okay. So again, we have everything all in terms of sine and cosine already, which is great. I will probably start with the more complex side here. So where do you guys think we should start? Okay, so let's start on the right side. Does anybody recognize this?
Yeah, that's the thing that we foiled.
Yeah, we actually just did this above in our tips and tricks. This is a difference of squares. So the big thing here, guys, is when you don't know what to do what you know how to do. And we know how to FOIL, right? What does this difference of squares FOIL out into equaling here? 1 minus sine squared x, yeah. If you want, you can FOIL it. You can do 1 times 1, and then 1 times sine x, and then 1 times negative sine x, and then negative sine x times sine x. That will get you sine squared. And the positive sine x and the negative sine x will cancel, and then you'll get this.
Or you can just like memorize that.
Yeah, or you can just know the difference of squares pattern and expand. So here we are FOILing. And I asked you guys to add something onto your sheet earlier, next to Pythagorean identities. What is 1 minus sine squared x equal to? Yes. So if we look back up here, we can see 1 minus sine squared x is actually equal to cos squared x. This is a rearranged Pythagorean identity. I asked you guys to add this to your sheet. So we're actually pretty much done, our proof. So we just have to say this is equal to cos squared x, and this is because this is a Pythagorean identity. And now left side equals right side, and we're done.
Wait, you wrote I-O?
ID. You guys don't have to write this. I'm just doing this for the purposes of our lesson, just in case people ask me. ID, just like identity.
Do we have to say that?
No, you don't have to. I'm just showing you for the purposes of this lesson, just in case people are not sure where I'm getting things. Okay? Okay, we're going to take a quick 2-minute break, and then we will finish up our last few examples. Yep. Wait, what was it? Oh, 8 ball? Sorry. Okay, so here's our next example. Here's what we've got. Oh, sorry. It would help if I unfroze the screen. There you go. So we're going to separate our left side and our right side. This is always the first step. Everyone can do this step. You rewrite and rewrite. All right. Everything is in terms of sine and cosine, so we're good on that front. We will probably start by working with our left side because I don't know if there's too much that we can do with 1 plus cos x. So we're probably going to start over here on the left side. However, I think part of this is not quite obvious as to what we need to do from here, right? Because we already have things in terms of sine and cosine. I can't really cancel anything. So where do we go from here? Is there any suggestions as to what we might be able to do?
We just go to the next question.
Don't skip the question. That's not a good step. Okay. Ivana?
Make sine squared x to 1 minus
That is a very good suggestion. So if you guys notice, so the key here is we actually want to look at where we're headed. So if I want to make the left side equal to 1 plus cos x, is there a sine x in the right side? No, there isn't. So I should probably work on getting the left side all in terms of cosine, right? So we're going to start by just replacing 1 minus cos x in place of sine squared x there. Okay, this is a rearranged Pythagorean identity. Okay, it's one of the ones that I showed you in your tips and tricks section. Okay, thoughts from here?
Do we cancel?
Ooh, can I? I can cancel separate pieces, right? So think back to your rational expressions training. You've been trained for this. Can we cancel separate pieces if we're adding and subtracting? No, we cannot. Okay, that's a no-no. Other ideas, what can we do? Isabella?
If you have, technically you have, can't you subtract it to get the positive on the other side?
No, because it's division right now, right? Good suggestion. I heard something. Zion? Okay, so on the top, I have a perfect square, the number 1, minus cos squared. So Zion, what does this factor into when I do difference of squares?
1 minus cos x and 1 plus cos x.
Beautiful. This is difference of squares. So we are factoring this time. We're not foiling, we're factoring. So kind of the opposite of what we did in the last question. Okay, thoughts from here? We're literally almost there. Ivana? Yeah, so I can cancel this group with this group down here, and I'm left with 1 plus cos x. Lovely. And now we'll do left side equals right side and box it away. Yay. Owen, can you put that away, please? Okay, one more example, and then you guys are going to do some practice yourselves. Okay, so we're going to start by just rewriting. Okay, and I actually am going to have you go back over to your tips and tricks here. There's one other little thing that I want you to add to your list here. I'm going to put it over here if you have some extra space. And that is, if you're adding and subtracting fractions, basically all of the time, you are going to combine those fractions. So find a common denominator and put them together. Okay, so we're going to find that common denominator. Once we have that, we're going to put those fractions together. That usually works most of the time. I don't want to say all of the time because that might not be true, but I would say in general, if you have two fractions being added or subtracted, we're going to try to put them together. Or more than two. Okay, so let's skip down to the bottom. Is everyone okay if I scroll here? We're okay? Okay, so first things first, do we have everything in terms of sine and cosine?
No.
Okay, so I'm going to start over here. What can we do to make the tan x in terms of sine and cosine?
Tan x equals sine x over cos.
Yes, tan x equals sine x over cos x. So we're going to replace that with its identity from our sheet. And I want to think of this bottom cos x. What's the denominator of this bottom cos x technically? 1. Okay. So I have a fraction inside of a fraction, and they're being divided. So fraction rules tell me I can multiply that 2 in there. Remember, this is like 2 over 1. So when I multiply that, it's just being multiplied into the numerator. But I'm going to flip and multiply this bottom fraction here, because when I'm dividing a fraction by a fraction, that's the rule. I can flip and multiply. And over on the bottom here, we will have 2 sine x, and cos x times cos x is cos squared x. So if you remember back, I touched on this a few lessons ago, but we don't usually write cos x squared because it's unclear as to whether it's this whole thing squared or whether it's just the x that's being squared. So we usually, if we want to write cos squared, we'll write it in between the cos and the x to show that it's the whole term cosine of x times cosine of x. Okay, just as a little tip for you. Okay, can I go any further with that? That's probably about as far as I can go. So this is my goal. This is kind of like where we want to always be checking back to as we're working down with our left-hand side. And I want to be looking back to that and saying like, okay, am I close to it yet? Am I there? Am I there? and we'll keep reevaluating, okay? So, oh, sorry, I accidentally put this as a plus. It's a minus. If you copied mine, then just make sure you fix yours. Okay, so biggest rule, find a common denominator if you're adding two fractions and you're going to merge. Hi, Mr. Shin. Yeah, for sure. Okay, so what's my common denominator between 1 minus sine x and 1 plus sine x? Sebastian? I kind of, like, when I have a grouping, I have to, it's the whole group or none of it.
1 plus sine x for the top and bottom.
Yeah.
Plus side, and then just opposite.
Yeah, so you can't take a piece of an expression. Like if you're adding and subtracting terms and it's like an expression, it's all or nothing. You have to take that whole expression. So just make sure that you don't take like any pieces of that. So I'm going to multiply that in on top and on bottom. And 1 times this is just 1 plus sine x. I'm going to leave this in brackets as I merge this for 1 second because I want to show you guys something. So they have a common denominator, which means I can just write them all together under 1 fraction or over 1 fraction. Okay, why did I leave that second part in brackets? Can you tell me why I would do that? What's that, Ivana? Yes, and in particular it's a negative, right? So that means that this negative actually applies to every term in this second part of this fraction over here. So I actually have to make sure I distribute that negative. So you guys are probably remembering back to some of our rational expression stuff, where when we did the subtraction questions, we wanted to make sure that subtraction got into every single term in there. Same deal here. Okay, so when I put that negative in, I get a -1, and my negative and negative here give me a positive sine x. Okay, I have 1 minus 1. Those are gone, right? That's 0. I have 1, subtract 1. Those are gone, right? They cancel each other. So what's sine x plus sine x? 2 sine x. Very good. Ooh, this is looking nice because look what I have over on the right side. I have a 2 sine x. Ideas as to what we can do to the bottom. Remember, we're headed toward, we want this to be equal eventually to cos squared x. So what should I do with the bottom here? Difference of squares, so we're going to FOIL. And when I FOIL the difference of squares, can somebody tell me what I would get here?
1 minus sine squared x.
Yeah, 1 minus sine squared x. Very good. So we're FOILing the difference of squares. Again, you don't have to put that. I'm just showing you for the purposes of our lesson. And look at where we're headed. So I want the denominator to be cos squared x. How can I do that? This, yeah, it's an identity, right? So it's one of the rearranged Pythagorean identities that I asked you to add to your sheet. And that was that cos squared x is equal to 1 minus sine squared x. So this is an identity that I'm replacing there. And now we're good. So we have left side equals right side. And we squared it away. No. Not particularly. Did that stop? I think it stopped, just froze. Hopefully that works. Oh no.
What's it mean?
Quite obvious.
No, you do not.
Girls don't.
I'm well aware.
Don't poop either.
Yeah, no, our bodies are actually designed where we don't